Hello everyone, we shall come back and continue our discussion on vibrations. So vibration, we have defined it as a to and fro repetitive motion, and repetitive motion is of two types. One is periodic motion and aperiodic motion, and in our discussion in this course is going to be the vibration which is periodic in nature. That means the repetitive motion is going to repeat the whole thing after a fixed interval of time, and that interval of time is called as a time period. After which time, how much time it is going to repeat, that duration of the time is called as time period. So say we have discussed one type of periodic motion, that is a simple harmonic motion. Simple harmonic motion we have discussed, and say mathematically we stated it as x equal to a sine of omega t. So x is the displacement, a is the amplitude, and omega is the frequency, t is any time t starting from 0 onwards, 0 seconds, anything. Then we have something what is called as frequency. We have defined it, the number of cycles per unit time, that is per second. That is called as the frequency, which may be expressed in hertz, or it may be expressed in radians per second. The frequency expressed in radians per second, normally we denote it by omega, and frequency expressed in cycles per second or hertz, that we shall denote it by f in our discussion. So we know that omega is equal to 2 pi f, and there is a relationship between f and t, the time period, and f is equal to 1 by t or t is equal to 1 by f. All those mathematical things, mathematically, once we start analyzing the analysis, then they are all going to be useful. But still we are going through a lot of preparatory work before we take off the analysis work, and we are going through a lot of such things, and a lot of terms also we will be introducing or we will be revising. Some of the terms you already know, and I just revise them and then make them aware to you and then introduce to you once again, and then I shall be using them later on. Okay, a topic which is mentioned in the syllabus, that is what I am taking today. So before this is a basic elements of vibrating system. So before that, there is something what is called as free vibrations. I have not introduced you to that. What is meant by free vibrations? Is there anything called as paired vibrations? No. All that I shall come back and then discuss. Okay. So as I said, earlier also I made a statement like this: anything which has mass and elasticity is bound to have vibration problem. So a machine which is vibrating, for example, then I want to make a study of that and try to reduce vibrations or try to reduce the bad effects of vibrations. For example, I had read somewhere, so there was some bridge which was built, all that, and because once the vehicles passed through, there was huge vibrations, considerable feeling, you can feel it. And even our earlier railway bridge, before the construction of that, I don't know whether you had any opportunity to stand on the bridge and a heavy vehicle going on at a higher speed, and you really used to feel the vibrations. So vibrations are very, very dangerous, and if they are allowed to go ahead, then we have a lot of problem. So therefore vibrations have to be addressed. For example, the bridge has been built, okay, and then before you really attack the problem, solve the problem, whatever the bad effects of vibrations, you solve that, you need to study. Okay, we call that bridge as a system. Say a machine which is having the vibrations, especially the big generators, if you go nearby that, you really feel vibrations. So all those vibrations, before you give a solution, you need to study. So for that, as I said in the beginning also, our course now is a very, very, very introductory one, and we won't be able to give the straight away the solutions. How the study can be made, vibration related study can be made, that's what we are going to study in this course. So any such study, if you have a system, a bridge is a system, machine, generator, all that, those we call them as system. We need to model them. Okay, there are different ways of modeling. Okay, so so when you are child, probably you used to make a clay model of a house, okay, school, then bus, like that. They are basically models. And the purpose, what is the purpose of that time? Probably an entertainment, that was the purpose, and that is why you used to make it, you used to make wheels, and if you are able to make a steering wheel, then probably the feeling what the one who has made the model, I think you should be able to imagine. So similarly here, we would like to study the system of vibrations, technical model. Okay, so we need to model it. So when I model it, so what are the different parts I need to use? That is what I am going to discuss now. Basic elements of a vibrating system. So a model, I hope you will be able to understand. Okay, there are so many models, physical model, mathematical model. You may not be able to see the physical model. Okay, say for example, I and you, okay, two friends, A and B are two friends. A has some money and B also has some money, and the money with them is less than 100 rupees. There is some statement. So I want to analyze it. It is only a part of the statement. Along with that, I have some more statements, and ultimately I need to solve the problem. Okay, what is that? A has some money and B has some money. The money together with them is less than 100 rupees. Okay, so how do you write it? So let A has X rupees and let B has Y rupees. Then you add the money together. What do? X plus Y. Okay, what is this X plus Y? The amount together with them, that is less than or equal to 100. X plus Y less than or equal to 100. This is what we call it as a mathematical model. This is a mathematical model, okay, for that statement, and probably which we may utilize while solving a problem. Similarly, the vibrating system, okay, vibrating system, if you model it, you will definitely need to use these four components. I am going to list them, four components, and those four components, which we call them as elements of vibrating system. Okay, so which are those four components? One is what is called as elasticity. The elasticity, and this is represented by what is called as a spring. Spring, which is normally indicated by what is called as a K. K is what? The stiffness of the spring. So how much? So spring is basically the one which undergoes elongation or compression. Okay, how much force is required for unit elongation or compression is what is called as stiffness. The stiffness, spring, okay, spring is normally represented by K. And the second one is what is called as mass. Okay, this I shall denote it by this, yeah, only then straight away the notation, there is nothing like this. And number 3 is what is called as damping. So I shall tell you, probably I am not very sure whether you have heard this word or not. I shall tell you what is meant by damping. And this I shall denote it by what is called as C. And the fourth one is what is called as excitation. Sometimes it is called as external excitation or in general excitation. Okay. So using all this, I have built a model, and that model looks something like this. It may be the exact reverse, or it may be in horizontal orientation or any inclined orientation. It doesn't matter. The orientation of this diagram doesn't matter, but these are the components that are essential to build. You don't need anything more than this. But sometimes my system, if it is too simple, then I may omit one or two. The omitting possibilities are only this 3 and 4. Okay, you cannot eliminate number 1 and 2. 1 and 2 components are must. You will definitely have, you cannot omit any one of them and build the system. That is impossible. The model shall definitely have spring and mass. But the system may have, so all practical systems shall have this. But my simple system, if I build it and only for the theoretical study, then that system may not have this damping and this thing. This is what? These two components are must and these are optional. May be there or may not be there. But for all practical systems, they will be there, optional. But for my study, these are optional. These components are optional and these are must. So please remember whatever the notations, etc., whatever I have indicated here for this system. And what is this kind of system? This kind of system, here the mass may come down or mass may go up like this. This is how the vibrations are. And these vibrations are what kind of vibrations? As I said earlier also, vibrations may be of two types. One is along the line, which are called as linear vibrations. Okay, linear or the longitudinal vibrations, motion along one line. Or I may have what is called as angular motion, angular vibrations like simple pendulum, the pendulum. So there also you require similar components, but only thing is instead of this, what is the type of the spring here? What do you see? It's the helical spring. Okay? The spring in case of the angular vibrations, we need what is called as, we shall call it as the torsional spring. The stiffness will remain same instead of force per unit deflection. So this K, so I shall have what is called as the torque per unit displacement. Displacement in case of torque is nothing but the angular displacement. The displacement there is measured in terms of radians. So torque, Newton meter per radian is the unit for angular deflection. Okay, anyway I shall come a little later to that, and I just want to mention. So for a complicated system, if the machine is quite complicated, I may have a number of these things. I may have a number of springs, number of masses, number of dampings, number of excitations. But I don't have anything other than this. If the system is too simple, I may have only one component, one spring, one mass, one dashpot and one excitation. I may have only that. That is maybe the system. So the number of units of these things depend upon the complexity of the system. If the system is quite complex, then I may have more number of systems. Then accordingly, the degree of freedom of the system also shall be changing. Okay, I have not discussed much about the degree of freedom. I had just defined, and I say that if I come back to the degree of freedom of this, okay, I say that this is a single degree freedom system. Okay, so what is the meaning of this? So the mass, the position of the mass, for example, when it is subjected to force, what is happening? The mass is occupying different positions. It goes, may appear, say one extreme position, and then comes back and crosses this and then goes and maybe some area, and then this is how it is moving. So where is mass? Where is mass at any time? So maybe after 0.1 second, tell me what is the position of the mass. Or after 5 hours, where is the mass? What is the position of the mass? So I want to know. So if I fix the position of the mass, say the mass is here, for example, then what I need to do? The spring is stretched and drawn, and this portion is drawn here, and that is the position of the system. So if you are able to identify the position of the mass in this system, then you are able to identify what is the position of the system. So therefore, how many variables are required for that? So probably I can imagine draw some reference here and fix this. So if the mass is here, then we say this is the reference, and if the mass is somewhere here, in that case, so where is it? How much is this distance? If I just know it, then that is sufficient. Say maybe I can have some sign convention. If it is downwards with respect to this, then I call it as positive. If the mass is above, then I shall call it as minus. So therefore, if I just say what is the distance, then that means one variable is sufficient, and that is why we say that this is a system which is having 1 degree freedom system. Anyway, I shall be discussing that etc. differently again. Okay, so what is the spring? So as I said, so it is basically a model. I don't take a helical spring and this is called as incidentally representing what is called as damping. Okay? This is also called as viscous type of damping. This is a helical spring, this is a mass. Okay? So I don't take one spring and one dashpot and this thing, not like that. Okay, there is no need to physically build the model of this. It is only in the mathematical model for mathematical analysis. I need to build this kind of system, and based on this the study is made, and probably based on this study you go back and address to the solution as a solution to the vibration of that machine. Okay, this is what we do, and there are four components. One is called as elasticity, which is represented by the spring, and the second one is mass. The third one is what is called as damping. What is damping? Damping is basically a resistance for motion. Okay, so if there is any resistance for motion, then we say that as the damping for the system. So if there is a vibration, if there is a resistance, if it goes down, no, there is something which is opposing it, then probably this motion may die out after some time. Okay, for example, friction. Say, imagine there is a body and which is moving on a road or on a table like that. Okay, if it starts moving, so because of the surface nature of this material and this tabletop or road surface, you know that there is friction. Friction is a must. When it tends to move, if I apply some force, and if that force is sufficient to overcome the friction force which is opposing, the friction force opposes the force whatever I apply. If it is more than this friction force, then only it will start moving. If that force is less than the friction force, then it won't move. Okay, though I am trying to move, why it is not moving? Because the friction is opposing. What is friction? Friction is a damping. Okay, damping is basically resistance for motion. If there is any such thing in our system, in our machine, then we have what is called as a damping component. And little later in this module itself, we are going to discuss various types of damping. What are the different types of damping? And so the damping, what I have represented here is what is called as viscous damping. Okay, what is viscous damping, etc., etc. I shall again come back. And what is called as excitation, the force. Okay, in IC engine, you are injecting the fuel air mixture or separately both of them, and you ignite it, or because of the compression the ignition takes place. So when ignition takes place, lot of pressure is developed, because of which you have force. Okay, that force. So like that force is transferred to so many components through piston, then connecting rod and crank, etc. So many parts it is transferred. So what is that force? So how much force? That is force is nothing but the excitation. So that excitation, okay, is called as the force which is responsible for the vibration is called as excitation. So any component which opposes the motion is called as damping. And mass is a must. Mass is there. And any system shall have what is called as elasticity also. We know that all members are elastic. And for example, say something like this I have. So I have a bar. So imagine I have a bar, and here I attach a mass to this. And this is of length L. And the diameter of this is quite small. Diameter is quite small. Okay. So now, how this is modeled? Say if I pull this mass and this mass is going to move. Okay, so your eyes may not be able to distinguish between these vibrations. They are so small vibrations because this doesn't extend so much. It is not like a rubber band. If it is a rubber band, then you pull this mass and this mass will go up and down. But if it is a rod made of steel, if I pull it, you won't be able to see, but it will really undergo some amount of elongation. And if I pull it and leave it, and it is really vibrating, this is vibrating. So if I model this, something like this, so how to model this? So here, as you know that any bar, if it is subjected to a tensile force, P, and its length is L, if A is its cross-sectional area, if E is the Young's modulus of elasticity, in the mechanics of materials, you have found out what is this, P, L divided by A into E. What is this? This is nothing but the change in the length of the bar. That is nothing but the elongation, delta L is equal to PL by AE. Okay, so then if I take this P divided by delta L, I shall take this and rewrite this equation AE upon L. Alright? Okay, P divided by AE divided by L. And what is this P upon delta L? What is P? Force. Force responsible for this much change in length. I want to know what is the force. This, if I calculate this, what is this? Force required for unit deflection, unit change in length. This is basically the force required for unit change in length. It is nothing but stiffness. So what is the K of this? So if I model this system, how does it look like? Okay, I have a spring. And what is this K? This K is nothing but AE divided by L. So you know what is D? From that pi d square by 4, that is A. E is the Young's modulus of this material. You know this material, you can refer to the handbook and get what is the value of E. And L is nothing but this L, the length. So from that you know what is K. And to this what you have attached? You have attached the mass. The system, if I model it, and this is how it looks. This is the actual system and this is the model. Why model? Model for study. Okay, I hope you understand. Here I don't have any external excitation, I don't have damping also, and therefore only the three component number 3 and 4 are missing, and I have only 1 and 2. And this is also called as a spring mass system. I don't have the other components, spring mass. Okay, I call it as spring mass system. Then if I also have a third component, then I call it as spring mass dashpot. What do you mean by dashpot? Dashpot is a representative of damping. So therefore in that case I call it as spring mass dashpot system. Okay, these are the different components. Please remember, whatever I have shown now, I have told they are all components of longitudinal vibrations. Okay, motion along a straight line, vibration along a straight line. Okay, if I have that, these are the components. Okay, even for angular vibrations, also I have the same title. The components are almost same, but slight change. Angular vibrations. Okay, the first one, elasticity. That is true again, it is a spring. The only thing is, it is not just called a spring. It is by default, if I say spring, immediate, by default understanding it is a helical spring. But I don't want to refer to a helical spring, I want to refer to some other spring, then I have to really mention that. What is that here? It is called as a torsional spring. Torsional spring. Now how do you get this torsional? You know this famous relationship, T by theta is equal to, T by IP is equal to G theta divided by L. Okay, this is famous torsion equation. And again rewrite this. What is this? T by theta, the torque required for unit deflection. If I write it It is G into IP divided by L. Okay, what is T by theta? T by theta is what is called as KT. Okay, K is a stiffness. And what kind of stiffness? Torsional stiffness. And what may be the unit of this KT? This is Newton meter per radian. And what is the unit of this K? This is Newton per millimeter. Because the displacement or deformation of the spring is very small, it is not in the order of meters. There is nothing wrong if you express it in Newton per meter also. There is nothing wrong. Newton per millimeter, Newton per centimeter, Newton per meter. That's how I can express it. But here it is usually expressed as Newton meter per radian. Okay, that is the thing. And in our angular motion, okay, so please remember, I think I shall come back and again discuss also Newton's second law. So Newton's second law, if I ask you or immediate thing what you recall is F is equal to ma. Okay, all our study or maybe related to our applications or motion along a straight line, therefore F is equal to ma. Remember, Newton's law is applicable for angular motion also. Newton's law is applicable for angular motion. So, what is the such statement for angular motion? So, if I say instead of force is required for motion along a straight line. And for angular motion, for rotation, I don't need force. What do I need? I require a couple or a moment or a torque. Couple or moment or torque. So, force is replaced by the torque. Okay, so therefore the left hand side it is not F, you can call it as C, the couple. C is equal to. So if F is equal to MA, so it is not M there, it is what is called as, okay, similar to what I have F is equal to MA, I have a similar relationship in case of a rotary motion which is equal to C. F is replaced by C, it is a moment or couple or torque. This is equal to M is also replaced by what is called as I. What is I? Moment of inertia. It is mass moment of inertia. Please remember, we have moment of inertia for area and also mass. So depending upon what is application. So in the study of mechanics of materials bending formula, so M by I is equal to sigma upon Y, something like that, no? So there I is area moment of inertia. So here what I am talking now is mass moment of inertia. So M is replaced by I and A is replaced by what? A is basically acceleration here. So this is linear acceleration and what is this here? Angular acceleration. What is angular acceleration? That is normally represented by alpha. This is nothing but radians. Alpha is in radians per second square. And what is I? I is mass moment of inertia. Its unit is kg meter square. And what is this C? C is the torque. This is basically Newton meter. Okay, so kg meter square radian per second square. What do I have? If I multiply kg meter square radian per second square, how do I get Newton meter? Okay, slight modification is manipulation, is not modification, manipulation. I shall rewrite it kg meter square, I shall write it as meter multiplied by 1 more meter and divided by the second square, I shall write it here. Okay, this is kg meter per second square. Meter per second square is what? Acceleration. Meter per second square. Kg meter per second square is what? This is Newton. And what is this? Meter. And eventually we have radian. Radian doesn't have any dimension. So therefore this also is Newton meter and this also is Newton meter. What is this? This is Newton's second law. So similarly here also, so whenever you are talking about the angular motion, so if you are talking about motion along a straight line, the mass of the body is important, that is sufficient. But when you are talking about the angular motion, the mass of the body is not sufficient. Okay, what is the what we require is moment of inertia. Moment of inertia. This is what we require. What is the difference between mass and moment of inertia? Mass is basically the quantity of the matter. How much matter is there in the body? So you know that matter. What is matter? Particles, small particles. Okay. So matter. How much quantity is there in a body, that is indicated by the mass of the body. Mass of a body indicates the amount of matter in the body. Okay, then what does this moment of inertia indicates? The moment of inertia indicates how this matter is distributed. How this matter is distributed, that is indicated. For example, imagine that I have a disc. I have a solid disc. And I take this, okay, its radius is some value, okay, and its mass is m. I take it in a balance and then weigh it, and its mass is m. Then if I find out what is the moment of inertia of this is equal to I equal to half mr square. This is what is called as the moment of inertia. So similarly, now I have another disc. So this is what is called as a rim type. So rim type means the mass is concentrated at the rim, and inside there is no matter here. This is all hollow. All this matter is here only. The mass of this also is m. Okay, the same. If it is 5 kg, this also is 5 kg. Okay, if this is 3 kg, this also is 3 kg. The matter, the quantity of matter here and the quantity of matter is here. Both of them are same. And this radius, and say this also is r only. But in this case, the moment of inertia is mr square. Okay, this can be easily proved, and you can, if you have time, you can go through it. Okay, here the same amount of matter has been redistributed in such a way that moment of inertia is different. So what moment of inertia indicates? Moment of inertia indicates the distribution of the matter. Okay, so this is important quantity parameter. And number 3, damping. And this is again called as the torsional damping. And number 4, what is called as excitation. Instead of force, here we will be having what is called as the torque or coupling. Okay, excitation. So these are the 4 components which are required to build any vibration system. I hope you have understood. And using this, we shall build various systems and then try to analyze them. Okay, so probably we can stop now, and then we shall continue in our discussion. It will take some more time to reach the analysis of this thing. Okay, good day.